problem I've just been working through is not a well-posed problem because the difficult bit's at the beginning. The rest of it actually is fairly straightforward. So the next question, which we haven't done, so I'm just going to tell you the answer, is use Hunt's rules to suggest the energy ordering of which these terms occurred. Well, some of you may have met Hunt's rule. The simplest one is maximize spin. So you'd expect the triplet states all to lie below the singlet states. The second rule is maximize L. And I think that, to be honest, I'm going to check that one, just before I tell you a lie. In molecules, which I normally deal with, you don't have to worry about L. So the third one is on J and is complicated, and I'm going to ignore it. So for a given configuration, the state with the maximum spin multiplicity is the lowest in energy, is the actual statement of Hunt's rules. For a given configuration, the spin multiplicity, the state with the maximum orbital angular momentum is lowest in energy. So it goes triplet F, triplet P, singlet G, singlet D, singlet S. Lowest is triplet F. Okay, and there are rules on J, but I'm not going to get into them because they're quite complicated. Actually, I may mention them. So that's the next bit of the question. Then it asks you to give J values. So singlet G, what J values can you have here? So you've got L equals 4, S equals 0. What's J? 4, thank you. Triplet F. You've got L equals 1, sorry, S equals 1, L equals 3. What J values can you have? 3, 4, 2, that's right. J4, J3, J2. We've done singlet G. What's the next on now? Singlet D. Singlet D is 3. Sorry, it's 2. Because D is 2. Triplet P. Any offers on triplet P? This is the commonest state of the lot, so you should know this one. Come on. 1 plus 1. 2. And 2, 0, and 1. Right, thank you. 2, 1, 0. The last one is singlet S, and that's trivial, that's singlet S0. So those are all the term values. 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. Are they odd or even? Sorry, they're all the levels. These are the term values. Odd or even? Any offers? What's L for D? D is so S is L equals 0. What's D? 2. So if you're 1 electron in a d orbital, is that odd or even? Even. So if you have 2 electrons in a d orbital, is it odd or even? It's still even, because 2 plus 2 is 4. So it doesn't matter how many electrons you have in a d orbital, it's always going to give you an even contribution. It's P and F orbitals that matter. So I haven't put any superscripts elements to range. So I think that's this problem. I'm now going to give you a different one. So if people have finished making any notes on that, can I get rid of it? Carbon. Be trusting you with this one. Configuration of ground state carbon is 1s squared, 2s squared, 2p squared. So what I want you to work out is what are the terms and what are the levels. And if you want me to come and answer a question, just stick up your hand and I'll wander around in a few minutes and I see how people are getting on.
Control. Okay. From this decent risky and wasn't you even to the going same so big and so there's wait should it and miss when we use so great instincts and benefits to and for fence close you quit on it. When Chinese use and it a bit of other instance but they could take it some use but wow and you're saying facts CDT to listen to listen we one but you see in this so and eat. I'll talk when since we just let's be asking you to do good this then but we say then most of is to my goodness cannot then they do it then so Robin the onions lemons the spoons it just needs but see I don't choose French seats and kind and I didn't say it. They said, "Does it please me?" This thing, and I like, I'm a symbol. Still, there's bring on symptoms to sell us. That can mean thing. Can I speak? Spoon, aim it at you. Questions? On the extreme one, but what do you mean? It's the tough range. Here. We bring that all the sauce in this looking much and eat and everything and that. So has then staying this to us screw this away and had this policeman. Texas years. You try to this man grabbing this to be something. Sir, interesting. See, I see you have this the Sunday party cut with that. Well, see, activities. It just, but you know, like this. So this is because there, to the others. Veterans. I mean, this. Second, the thing. Was these kid and she shy beauty. Each one will was where I keep the skill. Studying this way, no one's saying different years and so. So, then as well as no, so to do it, to the stuff. There was been the routine of the bad. The version. Focus on cheeks, but Addison and beer. I don't see that about this. Addison's okay. So it's so to us like with chip so white items for it is the chipster. You're saying, man, what did the good? So myself that they've got speed and the kid stars and hey, so his need was from the script. We were still witness. I did discuss select. Speak on spell swing. That to them help. Yeah, so not. So what we got when this like to know this started up to San Diego. This year I was using to get up this because they false. Okay. Wellness or this yeah. Is certain yes that was not at least that was I think that Pacific decided to use what's that everything doing? Okay. That the yeah, repeatable. That's ever something you get back even and there and went date. Then to get a smooth silver. There are certain things else you can do about this and it might need you don't have to hear it. Then got this we're not doing this with this fall. But that's yeah, that must be getting the next bit of push or cities who don't see twists collects or I think subject on them and this and it's a person that I forgot to there are two rights with this hobby either the deeds this but topic that they see and mention that just then begins trolls in the sound. We got this. He told me then I said the kind. Yeah, I said self against bad things. And then there's one. So this is just and that's true. You have to consider use that sponge as they can just them down diaphragms. My wife said the goes of person nothing in it. The paste. Why getting that? Then so this very awesome. Oh, it's cool. Right? So it was that certain food and sauce. So I wasn't expecting a couple of questions out of one question. So though you mentioned the last thing the biggest school we don't use it for long. You're in this it the amnesia so it's almost and then that concerns did it. But the book doubles question system for second edition line for myself. I didn't think that's part he's still in the line. The killing the instant. I'm spread the see that's something cost out seats because do that didn't understand. We second the two piece well, so you got Starman's different. There's two piece square out of very well that it done. Where's just that's exam 10 meters cross out the items. Good. Well, I have to say, when I was not too sad, when I got Judas Shivard, and we still had Kiki and cross over with the thing, Kate Westing. The anything not such to was actually goes me. Kate used to get and the thing into it. There, and it's not just so creepy swear. So I think I would we call it listening. To see was either is was each West Sunlands and questions again, yeah, the person in the case. Yes, and so we see other class with some today's work out of the just I can see that no didn't study. That's it. So yes. But it's not how to stop there since it feels like it was the same. Yeah, but nice for the each. That means what's a couple of plans of parts are not more than the best look see up what I doing that even shirts in our having done choose shirts your day. Say most should be say this and then it is total use the ocean and the rather this it is some of these so that's what management so that's the you find it was so you need to get big so give us a few goals. One thing is good. So you suppose what to show some other bus to all mine said as yeah, we do with time and I think look at see the switches is the it's right as it was on doing our defense for the stuff called Asa and thought he is that he was in fact figure for NHS very dish given is out loading. The starting thing you did out as a gear and also appears to lose that old music. That's thing to sing to get else. It's a one. So close by it's shadow. So you know, so you go second see. Because strike tracks and that sparking sounds. But I can't find the teeth. Yeah. And it didn't say being for our sense gaming, just to do me called mark to quite my sense. German sanitary solution. Yes, yeah, there is only to call it. It's how many things you like to do to rest. But you don't know that this easy in the face. So it's a person. Start this always getting into reality. Exactly. The truth stories. The brain needs fast episode. This again, just as a touch of what's again falling. Things that the ridiculous like and having the stake and the rest. So I always go chanting and just sure. So again, it is that fine. Don't know you're expecting of that. Final conclusion is meant to be a load of term I use for two piece stone starting. I think I wrote up there as a note for me. I'm going to do that after this torture. So we're not going to what should have is term values during the what I scratch your squared 2p squared. So what is of the test and one p put this that thing. So return values are never so this is the question you asked. What are the terms? What are the numbers? Okay? Yeah. It's one to give us this and she could get us a this but you know this crazy. This year, lens 13 is oh, but you know it. You live in your bed, usually distant. They find it into like this. It's they, yes, we. That's the place. Bringing that to I'm going to give people 5 more minutes and then we'll suffocate through the answers. So just finish enough of the other bit and force to go. Sit. I got to create a strong sitting on to the place she's empty. Wait. That's the call now. Smooth breeze. And the food. You'll have to slip on the musician and it is. Out. If the steam system graphing today's usually the said is by the sinks choice again, doesn't big go ahead. How's yeah, or stuff like it. Well, what was the need? This yeah. And that I can switch to formulate indications of indefinite passage in persons. Das schon nicht abgetan ist. Ein Chain Start. But it is really the things. Late diamond. It person. The scene that is this. You took in Spain. It was in my husband got my saying, and I was what can I still not take it for nothing. He was not really making some still edging. And it was careful on the place is the best sashes. It's a good no. You think it's a special edition. It's here stuff is it has an understanding. Yes, it's been sheet. I jumped the car is like very there's some kind of strike. Thing, in the close submersion, the homeless thing, so the skin of it, not the last time, but his no member that's also us. So the skin will come to clashing in this around, then you don't spell that. Well, so he will support this, one is stuck to a square, heavy, with his essay influences and fears. And they personally have to find them because I can talk a little bit of the okay. Yeah. Going to this, which means convey. In this, say to thyself in the MBOT. There's I don't think these things is need to make they come here, but was I am sorry, we're doing that. This day we speak on things. We just can't wait. That is it. Facebook saying these friends yet the phone thing, you know that. They just praise the world and let me get up. That the change. So sometimes and that though seeing and say we want to speak to much. And so that means surely then you must hear some possession. And it's for now and surely the things we need to get out in the homes. The same. Three God's piece of they spend in it. Though to me, it's God. God's the nice place of this. Nice, square it. For instance, months of shit jokes, that's our wings. Because I believe about part of the shaking. Local at the was the yelling. Now the nation used to harm. Easy. It's any as time. Kind of like it. He's a school in the feeling nothing. The street. The chief man said, two of the night. They tended to Germany. And he's living in the air. The Indians may take them to the other man. Because the theory to actually come there, some seats, diamond, unspeak, and we know, I can't say the man's been treating. Yes, it is, but it does be. I'll put the skinniness as an agency as well. When it came about personal countries, basically, and when specifically, must be like, this is the birthday. I don't know for it's been all connections will come together. I escaped the camera. This to be attending to us. To make this thing, I like ears and the pictures had to exist. And so the packing and rest to the issue. I think future objects and their posts.
Okay, I'm going to start going through the answers, or more to the point, I'm going to get you to start going through the answers. So if I remember where we are, you hadn't answered a question, is that right? Okay, so let's start with you. Where's my pen? So what terms can you get from this configuration? No, that's a level. 1s, 3 triplet p, and singlet d. Okay. So those are the terms you're allowed. Now, just a couple of notes on how you do it. That has L equals 0, S equals 0, so you can just ignore it. That is the same. So you just need to consider the 2p squared configuration. And if you had 2p squared on its own, you get, If you had 2p, 3p, you'd have S equals 0, 1, L equals 0, 1, 2. So you'd get, singlet S, singlet P, singlet D, triplet S, triplet P, triplet D. If you use what I call the cheats method and you go for the odd, you delete the odd ones where S plus P is odd. Sorry, I'm deleting the wrong one. You get rid of triplet D, singlet, triplet S, and you end up with those. You can get the same thing by going through looking at the states one by one and ticking them off. So can you tell me what terms? No. Next, your neighbour. Yeah. Sorry, say it again slightly.
Singlet is 0.
Yep.
Triplet P 0.
Yep.
Triplet P 1.
Yep.
And triplet P 2.
Yep.
And singlet P 2.
Singlet D 2. Right. Good. Right. Are you next in line? Question I didn't ask, but I answered just before the break. Which do you think is the lowest of those ones? We can do the terms, not the levels. No, so the lowest is the one with the highest spin state. So it's triplet P. And in fact, all three of this splitting is very small, so all three of these components come before the next one. What do you think the next load is? So we've got triplet P, what comes after that? Is it singlet S or singlet D? Sorry, that should be singlet S0. So no, it's after highest spin, it's highest angular momentum. So it's singlet D, and then it's singlet S. You've got three terms there. I said I wasn't going to tell you this, but I'm a glutton for punishment, or punishing you anyway. The reason why it's slightly confusing is it depends whether this shell is half open or half empty. So you can get 6 electrons in a P shell, so it's less than half full. And if it's less than half full, the order is lowest to highest, so it's 1, 2. If you do oxygen, which is 2s squared, 1s squared, 2s squared, 2p, that's 1s squared, 2s squared, 2p to the 4th. It's exactly the same as carbon, and you get it the same not by doing 4 electrons, because that's a pain. You get it the same by doing 2 holes. And it has exactly the same effect. So this gives you singlet S, triplet P, singlet D, exactly the same as carbon, but these are in reverse order. Gives you triplet P2 is below triplet P1, it's below triplet P0. So this is more than a half open shell, and then the highest J is lowest, and if it's less than half shell, the lowest J is the lowest. Right, so I was then going to consider some transition selection rules, so we need to bear in mind these things here, which are a bit messy. Those are our lower states, and I'm considering transitions to 2p4s, and 2p4s have these 4 term values. So if we start with singlet S, where are we in the row? You the next in line. Singlet S0, can I do a transition to that state by dipole selection rules? Is that allowed or not allowed? So this is, I'm sorry, I missed off something very important of this when I did the term values here. They're all odd, because you've got a P, one P and one S, so L equals 1, so they're odd states. So you've got a transition not from an even state to an odd state, so is that allowed? No, it has to be even to odd. For a dipole selection rule, it must be even to odd. So that's even to odd state. You've got transition from L equals 0 to L equals 1, is that allowed? Delta L, I think, has to be 0 plus or minus 1. So that's allowed. You've got transition from J equals 0 to J equals 1. Is that allowed? Sorry? Yep, delta J is either 0 or plus or minus 1. And you've got spin that doesn't change. Is that allowed? You think everything's forbidden. Everything's allowed. So this is a completely allowed transition. Okay? So if we then consider, so we're doing transitions from this singlet S state. If we go to triplet P0, what sort of transition is that? Is that allowed? So how about the spin? You're going from a singlet state to a triplet state. If you're going S equals 0 to S equals 1, is that allowed? Your neighbor who's good on disallowed transitions thinks that's not allowed, and she's right in this case. So this is so delta S equals 1 in this case. Okay, so that's already a problem. How about J? What's the values of J you're doing there? 0 to 0, and whereas delta J 0 is normally allowed, 0 to 0 is a special case that's not allowed. So this would make it an intercombination line, but this makes it forbidden. So this is a strongly forbidden transition. Delta J 0, 0 is a rigorous selection rule, so you don't get that. So if we do the next one, where am I on the row? You're the next one in the line of fire. So singlet S0 is a triplet P1. So where do you want to start? Spin, J, L? Spin, okay.
Delta S is 1.
Yep.
J goes from 0 to 1.
So delta J is also 1. So that's
That's possible.
okay.
This is not.
Okay. So this is actually an intercombination line. That's a weakly forbidden transition. Okay. Your turn next. So what have we got here? Delta S is 1, as with the other ones, yep. Delta J equals 2. So they're both not allowed. Delta J equals 2 is strongly not allowed by dipole rules. So that would be a weak quadrupole transition because it's spin changing as well. Okay, timekeeper, how am I doing? Is it time for me to shut up for the evening? We have 10 minutes. Oh, good, I can give you another problem. Excellent. I had another problem lined up. If we go back to my screen. Sorry, I do need to do this, but I also need to do now I'm a bit confused because what I'm seeing on my laptop here is not what I'm seeing there. Do I have to? Oh, okay, now what I'm seeing on my laptop has changed. There we are. Oh. Do I have technical support here? Why am I not seeing this on the screen? just need to carry on fiddling around with that. And actually, you won't tell whether it comes up if I write on here, will I? So that doesn't work. I can't tell you whether you fixed it. For some reason, my laptop stopped talking to the screen. It obviously thinks it's time to go home. Which is not my laptop, it's their laptop. It should be problem 2. That's right. It's okay, we're here. Just move that up the page a bit. So I'm quickly going to go through question 4, which is actually much shorter than question 3. And let's start by doing part B, and then I'll do part A for you. So part B gives us 3 term symbols, all of which are wrong. So I'm just going to go through around the class again. My timekeeper is the only person who's so far missed out. So can you tell me why you can't get a singlet F1 to level? So what you have to do is what is L here and what is S here, and then what possible levels can you get? No, S is 0 for L is right. So L is 3, S is 0. So the only J you can get is 3, not 1. Okay? Right. So where should we go? Who in the background wants to volunteer to start off with before I point my finger at someone? 0F 5 halves. What's wrong with that? Lady with the camera taking a photo. What's 0F? What's the problem with 0F 5 halves? Why is that unphysical? Yeah. So you need to do the same thing as you did the last one. F is what L value? 3. 0 is what S value? Minus a half, which doesn't exist. Okay? So it's unphysical because you can't have you have to have a positive S value. Okay? Gentleman next to her. Triplet D 3 halves. What's the problem here? So D means L equals 2. 3 means S equals 1. So S equals 1 is an integer. This is an integer. You can't get a half integer. Okay? So those are all silly numbers. Let us put down to see if people can spot why they're not right. Let's do the first bit. So we've got a term, quartet D 5 halves. This is an allowed term. That gives you L equals 2, S equals 3 halves. So the other, let's read what the question says. What are the values of LS and J for this level? How many states does it have? Let's forget about that because we haven't done states. So if you want to know, the answer is 2J plus 1 of those. So 6. What are the other terms? So you have L equals 2, S equals a half. That gives you sorry, what the other levels this term? I was going to say you can't have. So that gives you J equals 2 plus 3 upon 2, which equals 2 plus 3 halves is 7 upon 2, 5 upon 2, 3 upon 2. I think that's right. Is that right? No, it goes down to a half. It's quartet. So quartet, the number you get is there. It's a quartet. So you get D, quartet D, 1 half, quartet D, 3 halves. We already had quartet D, 5 halves, and you get quartet D, 7 halves. Okay, so that despite being the last problem on the sheet, was actually much simpler than the one I made you do or got you to do previously, but that's a problem. Okay, I'm not quite sure what the time is, but I think you've probably all had enough. It's been quite a long day. So I'll see you all in the morning. If you have any questions, do nab me or we can go through them tomorrow. We'll be on to the molecular vibrations. Okay? But anyway, right. So carrying on rotations, rotating some more. I already mentioned centrifugal distortion. This is just doing it slightly more formally. This is actually based on perturbation theory. So what you do is you assume the molecule is rigid. You can make a wave function for that, and then use perturbation theory to expand it. And there's no first order correction. The second order correction is this centrifugal distortion, which I already described, the thing about the spring on the spring holding two balls together. And that's normally represented by a constant D, and it's given a minus sign because it lowers the energy, and that makes D positive. And in fact, you go up in even powers of J plus 1, so the next term is J to the third, J plus 1 to the, and that's positive, and the next one is negative, and they alternate up. And one hopes they converge. Not always true. In water, they don't. In water, the series diverges, but I don't use these series. I don't particularly like doing it this way. I prefer going directly to the answer. But they are useful for understanding. So the spacing between the line lengths depends weakly on J, because D is normally rather small. So it's slightly less than 2B. And then both B and D depend on the vibrational state, because they're expectation values, not fixed distances. If it's not a rigid rotor, they're the expectations of the vibrations. So for a lot of practical purposes, everything you need to know about diatomic molecules, and this is not just rotational data, it's actually vibrational and electronic, is encapsulated by a book called Constants of Diatomic Molecules by Hertzberg and Huber. And I think this book was written before everyone in the room is born. You don't have to speak up if that's not true. So it's not exactly red hot up to date. But I have a copy of the book, but actually it's on the NIST website. If you go to NIST Chemical Web Book, it'll, there's a thing called Constants of Diatomic Molecules you click on, and you just have to put in the molecular formula, and I'll show you in a minute what you get. So you put in the formula, and you get you put in the formula first of the molecule, then you get constants of diatomic molecules as one of the options. And you click through, and you get something looking like this. And I don't know whether you can read that in the back of the room. Probably not. I hadn't thought of that when I put this up. Can I point to it? No. So I got here. So it's a list of constants, of which B and D are the two rotational constants here. And if you look here, this is the ground state of sodium hydride, and the rotational constant in wave numbers is 0.135 centimeters minus 1. The distortion constant is 3 times 10 to the minus 4, so it's 3 orders of magnitude less. So it's quite small. This constant here, alpha E and beta E, for which there aren't even values here, actually show you how the constant changes with vibrational states, but it's very small. I not going to go into it, but you can get the vibrational state dependent from that. There's also here the equilibrium bond distance, which is quite useful. And actually you get that. I talked about getting rotational constants being given by the moment of inertia times r squared, but actually it's the other way around. You measure the rotational constant, and that gives you r squared. So that's how the most accurate way of measuring molecular structure is rotational spectroscopy. You get your rotational constants. For a diatomic molecule, it's simple. You've only got one number. You only need 1b. For bigger molecules, it's slightly more complicated, and people use isotopes to get extra information. But basically, this comes from measuring that. So these tables, so things like TE we will talk about when we talk about electronic spectra. Omega E and omega E XE are vibrational spectra, so we'll talk about these in due course. This is all the symbols you got in there. So rotational constant, centrifugal distortion, internuclear separation. But do note that the data is only complete to the 1970s. Now, rotational spectroscopy actually had a very funny genesis, right, took off. So during the Second World War, the British developed a method to detect German planes using radar, which was pretty important for keeping London the city it still is, because we were getting bombed to bits. It turned out after the war that this allowed people to do rotational spectroscopy of molecules. So it's basically the radar equipment that had been developed during the Second World War got turned into peacetime radio analysis of molecular spectra, and similarly, rather similar stuff was used to look at molecules in space. So anyway, this book has no intensity information. The intensity is just the dipole squared, but they don't actually give the dipoles. For some molecules, you get a lot of information. So CO, there's the ground state. X is the ground state. We'll come back to this naming convention in due course. Rotational constant, nearly 2 wave numbers, 1.93 wave numbers. Centrifugal distortion, this is a rather rigid molecule, 6 times 10 to the minus 6. CO is a triple bond, rather rigid. Bond length 1.12 angstroms. There are 60 more electronic states, so there's a whole wealth of information in there, probably more than you want to know about. If you're actually looking for interstellar molecules, there are 2 databases, CDMS and JPL, and they're sort of twins. They're not twins. JPL is the older brother. So what happened was that JPL database, that's Jet Propulsion Laboratory in California, was started in the 70s sometime, I think, to catalogue all the rotational spectra needed for interstellar studies. A gentleman called Holger Müller went to do a postdoc there. German, he went back to Cologne and he started a database called the Cologne Database for Electrospectroscopy. And the original scheme was that I put them there complementary. That was if a molecule was in JPL, it wasn't in Cologne and vice versa. So what Holger did was collect molecules that went in JPL and put them in Cologne. Now, there was some logic to it, but it was slightly annoying because he meant you had to go to 2 databases to find one molecule. Unfortunately, that's no longer true because basically JPL hasn't been maintained for about 15 years. So now Cologne is beginning to get molecules where the JPL data was to date and needed replacing. So my short take-home message is use them in the order I've listed them there. If you don't find it in CDMS, then it's an important molecule. It'll be in JPL, but it's in CDMS, use CDMS. Right, I don't know. Oh, I know. Yeah, okay. So here I've got my cigar and my Frisbee. I knew I had them somewhere. So we've done the rotational structure of diatomic molecules and by inference, symmetric tops. I'm not going to dwell too much on symmetric tops because they don't have dipole-allowed rotational spectra. So there's not much point in spending a lot of time worrying about their rotational spectra. Sorry, spherical tops. I mean, we've done linear molecules and spherical tops. Symmetric tops can have dipoles, so we do need to worry about them. And now you get an extra quantum number, you get the projection of the rotational angular momentum onto the unique axis. So if we go back to this being my symmetric top, the unique axis is down here, and therefore you get the projection onto this axis of J, and it's normally called K, and it goes between naught and J, or actually you can have J, if you've got a fermion, you can have J as fermionic system, you can have J as half integer, in which case it would go half to J, with it half in steps of 1 to J, but basically, and there are actually two J plus 1 Ks, but they're degenerate if J is not equal to 0. Sorry, if K is not equal to 0. Say that correctly. Let's do it again. The K equals 0 energy level is unique. All the other ones are degenerate. In principle, there's a one with +1 and -1, +2 and -2, but they have the same energy, so you normally just give the absolute value of K. So there are two types, as I've said several times already, prolate and oblate, and they obey a rather similar formula, but it's not quite the same. So it depends which is a unique rotational mode. So in this case, A is the unique rotational mode down the axis, and then you obey this formula. In this case, C is the unique rotational mode. They tend to have a rather strong delta K equals 0 selection rule. So they behave with just the J's jumping with K not changing. But that's a phenomenological fact, not a provable one by just looking at symmetry. The rotational spectrum of asymmetric tops, conversely, are a mess. I'm not going to go into them in huge detail. So asymmetric tops, you have 3 separate moments of inertia. You can have changes in all directions. You can have delta J equals 0 transitions, because you get basically 2J plus 1 separate energy levels, some of which are odd parity, some of which are even parity. So providing you change the parity between the energy levels, you can have delta J equals 0. This is water in the terahertz regions, and it just had lots of lines there, so it's in absorption against some background here. And we were talking about optically thick. These lines are clearly optically thick, these ones aren't. You can assign this, it's possible to put quantum numbers on all of this, but I can't sit here and say this is J equals 2 to 3, Ka equals whatever. So it's quite messy. So you need a new notation. I've had more problems with it's not serious. Those funny boxes that have gone in there should be blank, so I've not lost anything. So you need a new notation here. You need, for asymmetric tops, you have to have projections on 2 axes. One is not enough. So I said already with the symmetric tops that the levels which had K not equal to 0 were double. In the asymmetric top, they're split. So you get 2J plus 1 levels instead of J plus 1 levels. So there are 2 notations. The standard one is Ka and Kc. So it's a projection of Ka on the A axis and the projection of K on the C axis. But they have a fairly strong rule that the sum of them can only equal J or J plus 1. So actually, for a given Ka, there's only 2 Kc values possible. J minus Ka or J plus 1 minus Ka. Or I put it there. Some of them is either J or J plus 1 only. They're only approximate quantum numbers, but they are generally used they're very, very widely used. There is an alternative, slightly older notation, which uses something called Tor. And Tor is the difference between Ka and Kc, and goes from minus J to plus J in steps of 1. So when Kc is 0 and Ka is J, you get minus J going all the way up in steps of 1 to when Ka is 0 and going the wrong way around. When Ka is J and Kc is 0, going plus J in steps of 1. So that's an alternative notation. You'll see it largely in older books. It's largely gone out of rule. So the selection rules, as I said, are delta J plus 1, minus 1, and 0 here. In principle, the other one says 0, but you don't tend to see them. For the symmetric top, you could get a transition that changes K only. And I think they are seen, but very, very weak. So this just shows you for water the three axes. So forget the top line, we'll come back to that tomorrow, I guess. The bottom here is the three rotations, and I look at this, and of course when you look at something in a lecture you always realize it's not quite right. This is not the center of mass. Center of mass is about here. So this line should go here. So if you have water like this is where it's nice when a lecture has a big rule in it. You know, water like this, the moment of inertia goes somewhere along here. If those are the two hydrogens, this is the oxygen. Then you have another one which goes the bisector. That's correctly drawn here. That's the b-axis. So this is the smallest moment of inertia. This, by the laminar rule, as it's out of the plane, it's the biggest moment of inertia. And the b is the intermediate one. So I promised you a little lump of interstellar medium spectrum. Here it is. There are no units on there, but I think they are hertz. There may be units on my slide. No, megahertz. Sorry, it's got cut off the bottom. And almost certainly, when I said that you get the diffusion limit with ALMA, I don't think this is the diffusion limit. I think this is noise. And that's just a function of the telescope, not that the spectrum isn't more detailed than that. But for instance, this is 1 to 0 of oxygen 17 substituted CO. This says SiO in its normal natural abundance, completely saturated. HCN, rather obscure molecule, SiC2. That's an asymmetric top, so you have Ka0, Kc5, Ka0, Kc4 there. C3S, an even more obscure molecule. That's quite a high level because this is quite a heavy system, so you get B is smaller. An unidentified line, if anyone wants something to think about overnight, to try and identify what it is. Vibrationally excited line for this polyene they're called HC3N with one vibrational mode excited. J equals 10. I don't know what the base molecule is here. Maybe it says so on my caption I've cut off. Oh, it's sodium chloride is the base molecule. Sorry, it's written up there. So these are the sodium chloride lines here. And you can see that they've lined them up so that they're all on top of each other, giving you the sodium chloride. I said to you already, sodium chloride has a very big dipole because basically it's a unit charge separation between sodium and chlorine. So you get these nice strong lines. And they all have a double peak. Anyone get me why they have a double peak? What's anyone know about chlorines? Isotopic abundance of. Well, I have a periodic table on my wall. And the periodic table under each atom tells you the mass. And if you read chlorine, it says 35.5. And I once had a paper to referee from someone who'd done a long list of HCl transitions using the mass 35.5. And I said, but there's no chlorine atom which weighs 35.5. And the reply from the author was, when I go to my periodic table, it says it's 35.5. And I said, yes, but there's no chlorine atom that weighs 35.5. Anyone know what the masses of chlorine naturally occurring chlorine atoms are? Okay, 35 is the most common. 75%, 25% is 37. So the average mass is 35.5, but there's no 35.5 atom. As you know, all the atoms are near. They're not exact integers because there's slight changes due to binding and relativistic mass effects, but they're all very near integer values. So what you've got here, and they're not very well resolved, they're pretty well resolved here, is 2 peak. And the smaller one should be the slightly heavier atom. Not true, because it would be on the red side, not the blue side. I don't know what the abundance of chlorine is in this particular object, but there definitely are 2 peaks in all of these lines. So, in fact, that one, the smaller one, I would expect to be on the other side. Anyway, that's because there are 2 isotopes of chlorine, 35 and 37. Sodium, I think, is all 23. I think it's not hasn't got any other stable natural occurring isotopes. So, you think you've done all of rotational spectra? Never forget hydrogen. The hydrogen has no permanent dipole moment. We've already said this many times already. HD has a very weak dipole moment. HD plus has a significant dipole moment, but HD plus is a real transient species because every time it collides with the hydrogen, you get H2D plus and it disappears. So I'm not sure HD plus, I think it has been seen astronomically, but it's not a big molecule. However, H2 plus is extremely common. If you think of Jupiter, it's basically a big ball of hydrogen. So is Uranus, so is Neptune. So even though it has no rotational spectrum, we have to consider the rotational spectrums. So it has a quadrupole allowed rotational spectrum. And that's about 10 to the 8 weaker than the dipole spectrum. So this is why for all other molecules, you forget it. Quite a lot of systems, there's 10 to the 8 more hydrogen in than other species you may want to look at. You now have new selection rules, which actually go back to the selection rules we did in atoms this morning. On J, there's the same selection rules. For a quadrupole, J can change by 0, plus or minus 2. You have the interesting situation is that because you get very long path lengths of hydrogen in space, certainly up until a few years ago, higher rotational spectra has been seen in hydrogen in space than they had been in the lab. Because naturally occurring, you get huge balls of hydrogen. You can get very long path lengths of hydrogen and see these spectra. And in the lab, this is more difficult, and hydrogen is rather explosive. So you don't necessarily want to fill up some meters and meters long tube with hydrogen in case your whole lab gets bang. Nowadays, they have cavity ring down spectra and you can fit them in small tubes, and maybe this is not true anymore. I'm not sure. B is very large, 60 wave numbers. If you remember, CO was slightly less than 2 wave numbers. That's already on the larger end for molecules. So these transitions don't actually appear in the radio or microwave frequency. They appear in the far infrared. So I put them in microns here just to change the atmosphere a bit. But 28 microns is something like 300 wave numbers. It'll be, they're not 2J, so I'd have to work that out. I don't know what these formula are. Right. I promised you nuclear spin statistics. Let's do it here. We'll come back to it later. Anyone know what the nuclear spin of hydrogen is? Come on, I'm sure someone in the room does. Googling it? No? Anyone know what the nuclear spin of hydrogen is? We've already discussed it in the first lecture when we look at the 21 centimeter line. Is it 0? How many particles does hydrogen have in its nuclei? You're not really that brain dead. 1, thank you. Any increase on 1, or are we all happy with 1? Okay. Do you know what the spin of a proton on a neutron is? Sorry? Spin on the electron. What's the spin of an electron? Right. So what's the spin on the proton? So they're all types of spin out stations. So we have 1 proton in the hydrogen atom. What's the nuclear spin? 1 gas correct. Nuclear spin is a half. So if you have hydrogen molecules, you have to consider 2 nuclear spins. half plus a half. In our excellent new maths, what's the sum of a half plus a half? 4, 0. Right. So you get two states, 0 or 1. Spin half, is that a fermion or a boson? Fermions, right. So fermions, there has to be fermions. If you remember your Pauli principle, have the odd to interchange. Okay? So you have to have a wave function here. When you change the two hydrogens over, the whole wave function is odd. So the wave function you can consider 4 components. And we're working through all these components. That's what this course is doing. Electronic, we haven't got to yet. Vibration is our next topic. Rotation, we're doing now. And what I'm saying is you also have to consider the nuclear component when you have identical atoms. I'll give you for free that for hydrogen, this is even, so we can ignore it. If you change 2 hydrogen atoms, the electronic wave function for the ground state of hydrogen doesn't change sign. For a diatomic molecule, it is always true for every diatomic. It's even, so we'll ignore that. So if we're going to make this thing odd, we have to worry about the rotational wave function and the nuclear wave function. The nuclear wave function has a parity -1 to the J. That's the equivalent of -1 to the L we did for the parity for the atomic case. So if we want it odd, for J odd, we have to have a nuclear wave function which is even. And for J even, we have to have a nuclear wave function which is odd. Okay? One of those is odd and one of those is even. Now, I don't know whether anyone has done this for electrons, where you get singlets, for instance, in helium, you get singlets and triplets, you get electron wave functions, normally written in terms of alphas and betas. I have a new Chinese PhD student, and we started talking about this and he got extremely confused, so he clearly had not done it. But normally for electronic wave functions, that is a singlet, and a triplet, by definition, has 3 possibilities. And alpha is spin up and beta is spin down. People met this in some form? I see a few nods going around, a few shaking heads. This is how you do electronic wave functions. And actually, knowing no more than this and the fact that I wish I could rub out on this thing. I make too many mistakes. So knowing no more than the integral properties are that alpha alpha and beta beta overlap perfectly, and alpha beta and beta alpha completely don't overlap, you can get exchange integrals out of this, which is, you probably know, a whole force that you don't get classically. So you don't need to know much about spin functions, and similarly, exactly the same in nuclear spins, we don't need to know much about them. Anyone want to speculate on, so we have singlets, we have triplets, which one's odd and which one's even? Odd or even? We're talking about changing things over. Does this change sign if you change the 2 spin functions? Nope. Does this one change sign? Yes. So this one is odd, and this one is even. Okay? So it's exactly the same with nuclear spin. This is odd, and this is even. So if J is even, you have to have I equals 1, If J is odd, you have to have I equals 0. And effectively, if you don't things like the 21 centimeter line, which, if you remember, was a nuclear spin flip, but had a lifetime of the universe, was incredibly weak. If you don't allow for those things, you have two separate molecules that in the gas phase do not change. They stick to walls and they reform a different hydrogen and so forth of thing. But if you stay strictly in the gas phase, these things behave as if they're two completely different molecules. So they're called, so which of these is most likely? Do you think you get more of the odd? I've written this the wrong way around, haven't I? Sorry. So that's odd, goes with even. That's odd, goes with even. So the product has to be odd because they're fermions. I'm really cruel. I'll get you to do this for deuteriums, which is a very similar process but different because deuterium has a spin equals 1. It's a boson. So which of these is more likely? Which has the greater degeneracy? Anyone? What's the degeneracy of something with I equals 1? And do you remember the formula for all angular momentum? Sorry, I haven't given you this in general. I've given you for J is 2J plus 1, but that's completely general for all angular momentum. So it's 2I plus 1 is the degeneracy. So the degeneracy for this is 1, and the degeneracy for this is, so these J odd states are 3 times more likely. That's at high temperature. At low temperature, because the J equals 0 is even, if you go low enough temperature, you get everything in the low state. And they're called ortho and para. That's why that's not. And it comes from orthodox being most likely and paradox being less likely. I always tell my Russians it's like Bolsheviks and Mensheviks. Bolsheviks means orthodox and Mensheviks means paradox. So a lot of molecules have this property, and basically things with identical atoms have this property, and you can get more complicated. C60, which has 60 identical carbon atoms, if they're all carbon-13, you get 5 different nuclear spin isotopologues. And we'll see this when we do vibrational excitation tomorrow. We'll see the effect of the orthopara directly in the spectrum. So they alternate. You'll get 3 times as many as these odd states and these even states. And I did many years ago, I did a little bit of work on comet spectroscopy. And we were looking at water spectra from comets. As you know, they're dirty snowballs. And they're very difficult to see from the Earth because the Earth in the water atmosphere is a big mess. But people found out this clever technique that because comets have sunlight going on them, the comet water absorbs light from the sun in the red or the near infrared at high energy, and then it cascades downwards. And they knew that because they knew where the energy levels were. They could find the lines, but we calculated the Einstein coefficients for them. When they fitted them, you get a rotational temperature, and you also get an orthopara temperature. But water has 2 identical hydrogens, so it's exactly the same. Turned out the rotational temperature was about 50% higher than the orthopara temperature. So rotationally, it was thermalizing, warming up quicker than the orthopara was. Why? I don't think anyone still knows that answer, but it was an interesting observation. And in astronomy, there's the beginning of doing interstellar chemistry with orthohydrogen and parahydrogen treated as 2 separate species with different rate constants for all the molecules. Sorry, we went on a diversion there. I went off on a slight side issue, but I did promise I'd do that. Right. So there's the rotational spectrum of hydrogen. Seem to have suddenly gone back to isotopologues. Sorry, I need to... People finish with my scribbling on here. Can I clean it off? Oh, come on. Okay. I think we've done this, but I'll repeat it anyway. It's important. So isotopologues. This depends on the moment of inertia. R is the effective bond length. If one assumes that which is true within what's called the Born-Oppenheimer approximation, that the effective bond length of all variations of CO is the same, the only difference in this rotational constant comes from using this reduced mass formula. So if you go from carbon 12 to carbon 13, you can see that you get changes at the, 0.3%? Sorry, 3% level, something like that, 2% level. So it's quite significant. So there are 3 different isotope modes. And this, as I said already, this gives the most sensitive method. Right, so I've already introduced nuclear spin. In principle, you can get splittings of that hydrogen spectrum due to nuclear spin. In practice, it's not very strong. But for some other molecules, nuclear spin effects in nitrogen are much bigger than hydrogen. Nitrogen has a nuclear quadrupole, and the quadrupole splitting in nitrogen is much bigger than the dipole splitting in hydrogen. So nucleus of hydrogen is spin 1 and has a big quadrupole moment. So you can see, if you use very high resolution telescopes, you can see the hyperfine structure quite easily in HCN. And actually, I got involved in a project a few years ago looking at why the hyperfine lines in HCN were differently populated. And we did all sorts of electron collision studies to see if that was the cause of it, and we got absolutely nowhere. And about the time we finished, someone showed that it was just a rather strange radiative effect and nothing to do with the properties of the molecule whatsoever. So my student wrote a nice paper on this, but it went nowhere because it wasn't really relevant to anything. Sometimes happens. So a molecule which has both I need to do this, don't I? Molecule which has both the rotational spectrum and fine structure and hyperfine structure is OH. And OH is part of the glorious 4. So until I talked about how radio astronomy came about as a byproduct of work on radar, before then there were 4 molecules known in the interstellar medium. Those 4 were all observed in the 1940s, and they're observed actually through their electronic spectra at visible wavelengths. They happen to have, they're all open shell species. Actually, yeah, they're all open shell species. So they had visible spectra you could observe they had electronic spectra you could observe in the visible, and people saw rotational transitions against. And so OH is a very vulnerable interstellar molecule. But it turns out its rotational spectrum is rather complicated because we've almost entirely concentrated on closed shell species so far. OH is not a closed shell species, and probably this symbol doesn't mean very much to most of you, but I'll go through it in detail when we do electronic spectra. But this is a doublet pi ground state. That means it's got an orbital angular momentum. This means it's got a spin angular momentum. They can couple together to give you a J for the electronic angular momentum, which actually is not called J. It's a projection of J on the axis. It's called lambda, 3 halves and 1 half. So you effectively get 2 different electronic states, not split by very much. I can't read on this thing. I can't inverse that at 79 weight microns, enough to tell you how much they're split by, but it's not very much. And then you get the fine structure due to the electron, and that gives you this splitting. And hydrogen has spin half, as we've all just discussed. Oxygen 16 is spin 0, so you can forget that. So you get hyperfine structure added on top of it. This is the last figure in my book, for rather obvious reasons. And it's really quite complicated to actually go through all these angular momenta, but just to show that you get some rather rich spectra. If you want a little story about this one, I've already mentioned Hertzberg. Hertzberg was really the founder of molecular spectroscopy. And he got a Nobel Prize very unusually, effectively for a lifetime's achievement. Most people get a Nobel Prize for doing one fantastic thing, and I'm going to talk on Friday briefly about someone who got a Nobel Prize during their PhD. Certainly wasn't for lifetime achievement. In the 1950s, when only these four molecules were known, Hertzberg did an analysis of the CN spectra, which only 3 lines were seen, associating going from J equals 0, J equals 1, and J equals 2, but that was enough to give a temperature. The temperature he got was approximately 2.7 Kelvin, and his paper says this is of no significance. How could he have won a second Nobel Prize? Anyone know what he was actually observing here? It took about 10 years later that someone discovered this. I think the number now is 2.6 Kelvin. Do you know what happens at 2.6 Kelvin? Sorry?
So, every birth.
No, there's something related to the Big Bang. B, the cosmic microwave background. So basically the universe has a temperature which was very hot at the Big Bang and has been cooling down as the universe expands, and round us is about 2.6 Kelvin. And there's been these whole telescopes, COBE, and there's more recent one, I don't remember what it was, mapping it out and discovering that it has interesting shapes and trying to get things. That was the first measurement of the cosmic microwave background temperature, but he didn't realize. And Wilson and Penzias recorded it in their radio telescope in 1962 or thereabouts. And if you remember the story, they couldn't believe that they were getting a permanent background observation, and they thought it was pigeon shit in their telescope receiver, and they went and spent a day cleaning out the receiver, and they still got the same number, and then they realized it was actually from out there, not as a source of their telescope. But Hertzberg had actually already found that number, but didn't realize it had any meaning. Nowadays, CN is used as one of the proxies for measuring the cosmic microwave background, and it gives a subtly different number from everything else. But I don't want to divert too far from what we're meant to be talking about. Okay, I don't know, timekeeper, how am I doing? Yeah, how much is some?
Oh, thank you.
Okay, so I think you're going to get less lecture and more problems.
Sorry. Yeah.
Yeah, so I think the rotational spectrum is all I want to do, but I think I do want slightly more than an hour for problems, so that's fine. Sorry, I've lost the last slide again. I keep on forgetting to do this. Bobby did warn me. There we are. So that's your take-home message on rotational spectra. Need a permanent dipole moment. Selection rule basically is delta J as 1, is go up in ones or down in minus ones for most cases. The intensities depend on the square of the dipole moment, and you see them radio to far infrared. The lighter the molecule, the shorter the wavelength or the higher frequency of the transition. So very big molecules are right down a very long wavelength. So SK is hoping to see some quite big bio-type molecules, well, what the astronomers call biomolecules, 3-4 carbons in them, very long wavelengths. So that's a bit you need to remember from this bit of the course. So I think what I'll do is I'll do a work problem now. Then we come back. I'm going to give you a similar problem to do on your own. So I'll do the work problem myself, and then I probably need to put a blank slide on the end of the talk. Excuse me a minute to do that.
Here it is.
Actually, I have it. Having said that, I also have it written out somewhere, so let's get that up first and then I'll do the blank slide. I'd rather hope there'd be a scribble on board here, but there isn't, so I'm going to have to just get it up. Problems 2. There it is. Come back to what I wanted. Come on. Not lecture 2. Sorry, I'm in the wrong place. That's the problem. That's my cause of the problem. Sheet. In fact, I think I had it open already down here. There it is. Right. Make that bigger. Still not very big. Make it bigger. Anyone see the... Sorry? Oh, yes, thank you. Which one is it? That one down the bottom, magnify here around there. It's this one. Too big. Go back, please. Okay. Can you read that at the back of the room? So it's number 3 we're going to do. We will probably do 4 and 4 as well, but let's do number 3 to start off with. What I want to do is number 3 for the break. Then I'm going to set you actually a slightly easier but more important problem afterwards. So an excited helium atom has a configuration 2 electrons in the 3D orbital. So this is a completely artificial problem. What values of total orbital angular momentum L and total spin angular momentum S are allowed? Okay, so that's what we're going to work out. Use spectroscopic notation to give the terms which arise from the combination of L and S allowed and the Pauli exclusion principle. So this is important. We've got 2 electrons in the same orbital, so not all the configurations are allowed, or not all the LS possibilities of the term. For each term, deduce the allowed value of the total angular momentum quantum number J. So we're going from terms to levels. Hence, give a full description of each level, including parity, using spectroscopic notation. Which level? I'm not going to worry about which level has less. I will tell you that, but it's not something we've done. What I'm going to worry about is transitions. So we'll look at some transitions with those levels. Okay? So if I flip the lecture, come on, don't do that to me. Stupid thing. How did I get color, anyone? That's that, okay. Gotcha. So basically we have a D2 configuration. I'm going to start by solving a different problem, which in some ways is easier, in some ways is more complicated. So I'm going to start by solving a problem. Instead of saying we have 2 electrons in the same orbital, we have 2 electrons in different orbitals, but with the same quantum number. And then we don't need to worry about exclusion because they're in the electrons have different ends. So we have L1 equals 2 because it's a d orbital, and S1 equals a half because it's 1 electron, and each electron always has spin 1. We have L2 equals 2, S2 equals a half. They're all identical. So what you want to do, and this is so-called LS coupling. So we want L equals L1 plus L2, S equals S1 plus S2. We've already done the second when you have 2 electrons together. You can get 2 answers. Anyone going to tell me what they are? 0 and 1, that's right. So that one's easy. We've done it several times ago. You get several times already. You get singlets and triplets. 2 plus 2 gives you quite a lot of possibilities. 0. Right, okay, so it gives you 5 possibilities. Probably stretch our Greek alphabets a bit further than we know how to go. Actually, we don't need Greek alphabets for this. That's when we get to molecules, so it's all right. So those are the possibilities. So in this case, you get all possible allowed combinations. So you get singlet S, singlet P, singlet D, singlet F, singlet G, triplet S, triplet P, triplet D, triplet F, triplet G. So you get a lot of possibilities. Okay? Half of those are not allowed by the Pauli principle. And there's a cheats way of doing it, which I'm going to tell you, and then I'll do it the formal way that I've always done to derive it. Cheats way is, and I think that's right, it's not in my book, I don't think. But we will prove whether it's right or not, because I'll do it the proper way. So that means 0, 0 is okay, but 0, 1, for instance, is not okay. So let's change colors. So that's okay. So for 3D squared, where they have to satisfy the Pauli principle, that one wouldn't satisfy the Pauli principle. But I think we're going to end up with those, but let's do it properly and we'll find out. Now, my preferred way of doing it properly uses boxes. So we have alpha and beta, which is half plus half minus half for the two spin states. So these, as you know, that's ms. So it's projections of the spin, plus and minus a half. And then you have to look at ml, the projections of L. And for D, there are -2, -1, 0, 1, 2. So we have 10 boxes. And the Pauli principle says you can only have one electron in any box. And so just a very simple way of doing the exclusion principle. One electron, two electrons cannot have the same quantum numbers. So we can get all the configurations that have two particles in different boxes. We can't get any which have two in the same box. Now, I'm going to deeply regret that I can't rub out of this place, because the convenient thing is put ticks in the boxes and then rub them out and start again, but I can't do that. So we'll see how we go. So if we start off with one particle there, so that's alpha, -2. The other possibilities we can have is -1 alpha, 0 alpha, +2 alpha, I've done this in the wrong order, +1 alpha. So those are the, there should only be 4 of them. What have I done wrong? You can't have that. Sorry. That's not allowed by the Pauli principle. That would be 2 particles in that. Sorry, and then I'm not doing this very well. Let's start again. We have -2 alpha. Then it goes with -1 alpha. -2 alpha goes with 0 alpha. -2 alpha. I'm going to get quite a lot of these, by the way. Goes to 1 alpha. -2 alpha goes to 2 alpha. That's right. So we got 4 of them with the alphas, and then we get 5 of them with the betas. Get -2 alpha, -2 beta. So that's partially in that box, partially in that box. -2 alpha, -1 beta, -2 alpha, 0 beta, minus 2 alpha, 1 beta, minus 2 alpha, 2 beta. There should be 5 of those, so we've got 9 so far. We're going to end up with something like 30, by the way. So we then say, right, so we've done that one. We've got all the possibilities of that box, so we can blank out that box. We can put a particle here. And go through the whole process again. Minus 1 alpha, 0 alpha, minus 1 alpha, 1 alpha, minus 1 alpha, 2 alpha. And same as this lot here, minus 1 alpha, minus 2 beta, minus 1 alpha, minus 1 beta. I'm going to need a bigger whiteboard. Minus 1 alpha, 1 beta, minus 1 alpha. Sorry, I've got 0 beta, 1 beta, minus 1 alpha, 2 beta. Okay, so we've got 17 and counting. We've done that box. 0 alpha, 1 alpha, 0 alpha, 2 alpha, 0 alpha, minus 2 beta, 0 alpha, 1 minus 1 beta, 0 alpha, 0 beta, 0 alpha, minus 1 beta, 0 alpha, minus 2 beta. So, they are getting smaller as we go through them. Okay. Next one is this 1 alpha, 2 alpha. That's the only one we can have left with the alphas. Then we get the beta ones, 1 alpha, minus 2 beta, 1 alpha, minus 1 beta, 1 alpha, 0 beta, 1 alpha, minus 1 beta, 1 alpha, minus 2 beta. That's that one. 2 alpha can only go with the betas. Minus 2 beta. So, getting worse and worse here. 2 alpha, 1 beta, 2 alpha, 2 beta. Right, so we've done all the ones which are pure alpha, have an alpha in them. We only need, I just wondering when I skip the other ones, I'd probably not. Let's do them quickly. So we need the ones which start minus 2 beta. They're not so many now, we're getting less of them. So we have minus 2 beta, minus 1 beta, minus 2 beta, 0 beta, minus 2 beta, 1 beta, minus 2 beta, 2 beta, 0 beta, 1 beta, 0 beta, 2 beta, and one last one, the last 2 boxes left, 1 beta, 2 beta. Okay? So those are all our possibilities. And what we have to consider is we have these various terms. We need to consider the projections of them. And what you do is you consider with the largest projections in spin are the case where you get either alpha, alpha, or beta, beta. They give you spin 1. So let's concentrate on the largest projections in order of angular momentum. And they have to be either 2,2 or minus 2,2, which give you L is 4. So I'm going to change color here. Let's do it in blue. So this one is -4. ml is -4. And somewhere there should be an ml, it's +4. It will come in... Can anyone see it? I can hear murmurs. Left at the bottom here. This one?
Yes.
Okay. Those are the only two, I believe. What they tell you about the spin functions, looking at them. What are the spin functions? They alpha or the alpha beta? They're both alpha beta. So this only goes with spin 0.
So what we have actually is
This state here. And that should have, G is L equals 4, should have 9 components, all of which are spin 0. So you can cross out, it doesn't matter how you do this, you cross out 9 components with spin 0, starting with L equals +3. So you then need, +4, then +3, then +2, then +1, then 0. So I think I've crossed out. No, gone down to 0. So I need -1. Where's something with -1? Alpha, beta. As I say, it doesn't matter which ones I cross out because I'm just counting here. -1, 0 would do it. No, that's all for alphas. I need an alpha, beta. Sorry, I'm standing to, that's alpha, alpha. That one's -1 alpha, beta. Then I need a -2 alpha, beta. Is that the lot? Is that enough? 1, 2, 3, 4, 5, 6, 7, 8. I need 9 of them if I missed. So got -4, +4, +3, +2, +1, 0, -1, -2, I need a -3. That one's -3. So it's 9 components knocked out. Okay? There are no other possibilities of making a G state, so I can't make the triplet G. The next highest angular momentum state we want to look at is F. That has m equals 3. I have some m equals 3 components here. Here's one. That one's m equals -3. I should have m equals +3 somewhere. Someone can probably spot it, this one. I probably have some other ones. That's an m equals -3. That's an m equals -3. No. And what's the other ones? There must be some more here. There should be 3 plus 3, 3 minus 3s, I think. So there's a +3. There's a +3. How many am I doing? 1, 2, 3, 4, 5. I'm missing one. I'm missing minus 3. There should be a beta beta somewhere, minus 3 somewhere. Must be here somewhere. Anyone see it? Beta beta, where the two numbers add up to minus 3. So it would be, it would be this one, would be here, come from there, from that. So I started with beta is minus 2 in the left-hand one. Oh, that's a beta beta, alpha beta, alpha alpha. So I got all the minuses. Beta beta, alpha alpha, it's alpha beta plus 3 I need. So that would go in the very original ones I started with. That's all. 1, 2, 3, 4, 5. 5. Sorry, I can't. Standing near the board, it's difficult to see this. I've got alpha beta minus 3. Got beta beta minus 3. I've got alpha alpha. Have I not got alpha alpha minus 3? I've got alpha alpha plus 3, alpha alpha, beta plus 3, and I need alpha beta plus 3. I've lost. It's got to be on here somewhere. I should have on which the alpha, either it's alpha plus 2, beta plus 1, somewhere. It's somewhere in there or I'd missed it. So you should get 3 each of these, which basically corresponds to the triplet. So the triplet, you get alpha alpha, alpha beta, beta beta. This corresponds to this term here. We can go on. The next one should be m equals 2, and you'll get 5 of them, and then it'll be the singlets. M equals 1, components, be 3 of them, and you'll get the triplets and so on. So you go through decomposing it like this. I've given you a long one. I'm going to give you a shorter one, so I'm going to get you to do doublet P instead, which is much, much shorter. But I think at that point, we'll have a break. I'll come back and do the rest of the problem for this case after the break. Okay. So let's take 5 minutes, just as I don't think there's any refreshments out there, but just to stretch legs and people need to use the toilet or anything like that. And I didn't mean it to disappear, but it has done.